Good evening, everybody. Welcome to League of Extraordinary Inventors. I'm your host, Mike from Faraday Research. I am doing the show live from a campsite tonight. It is August 1st, 2025. Welcome to the show. We got our usual panel
There's
on
some
tonight.
echo.
Oh, some echo. Oh, maybe it's somebody else. Shouldn't be me. I'm using a headpiece. But anyways, yeah, we have a special guest, Sky. He's
Hi,
going to join us tonight, and he'll be doing a presentation. But
Quantum Gravity.
as always, we have Lulu, and we have a regular panel, Philip. We got somebody. That's private chat. Okay, we're good. Yeah, so we got Philip, and we got Lulu, and we also got Bernie, and he's going to help out with the stream tonight because I am basically in the middle of nowhere. So yeah, live chat is open. So if you have any questions, comments for the cast tonight, please do so in the chat. Also have it showing up on the main screen there, so you can see the live chat as it's happening. And Mr. Philip, good evening. How's your week been? Philip, do we have Philip?
Hey, can you? I heard some echo. So is the sound fine now?
Yep, yeah, you're good.
Good. Okay.
Yeah, go ahead. The floor is yours.
Yeah. So I had the good week. I mean, I talked to the US Navy and they basically want everything to be peer reviewed and public before I work with them. So I said that doesn't make sense because I, I cannot make the trade secret public. So I don't think I'm gonna move forward with them. But on the other hand, I was accepted by the NVDA ecosystem for my software, which is awesome news. So I'm gonna have a much greater visibility.
Cool. Sounds good. So have you got any major feedback on your paper yet, or
Yeah.
have you got any feedback
Yeah,
on your
the
paper?
paper was for the U.S. Navy, but they want more than just one paper.
Like what? Like what do they want to know?
They want my papers to be all peer reviewed and public, so it's gonna take forever. And
Well, isn't that what I thought you just did?
yeah, but the paper that got published, the paper that I just published is not about the antimatter or the force fields or the stealth propulsion. It's about the galactic rotation curve. So uh, yeah,
Right on.
there's a
So
there's echo on some. I can hear myself twice for some reason.
somebody using a speakerphone? I'm using a headset.
Weird.
Ben,
Would it
how you
matter?
been?
Would it matter how it's connected to the internet? Like whether it's Wi-Fi or LTE E, or would it matter with the echo?
I removed Bert and Ernie, and hopefully that stopped any echo, or are you still hearing echo, Phil? You're muted.
I don't hear any echo at all.
You don't have echo here, so maybe the problem is me.
Yeah, it's got to be you. I don't hear any echo. Maybe check your settings for echo cancellation. All right. Well, as we're started, Mike's camping. The sun is setting, and we have Sky with us. It was Phil presenting, or does Sky want to go? Or
Sky, yeah, me. Nice to be on here. Does this screen sharing work? Okay.
This one or the other one? That one?
Yeah, this is the right one. Yeah. So this is, by the way, this is a painting about my theory. It's German Elementarräume. It means elementary spaces. Those are the space quanta of my theory, as they should exist in any theory of quantum gravity. So I started this theory in 2003, but the main part is actually 2005. This is dealing with, at the beginning, just with quantum mechanics, what is a superposition? And so the idea was that it's not the particles that are fuzzy, but it's us. We are in all the worlds that are indistinguishable to us at the moment. So we don't know if this particle is here or there before we measure. So it's in both places at once. So basically, I took the phase space where every point represents the state of the universe in one moment, and I extended it into a cloud, because it cannot be a point. There's uncertainty, so it's like a cloud. Many people say that the Copenhagen interpretation, which says that consciousness is central, that it could lead to solipsism, because I have to observe you in order to exist, and you have to observe me. And that's kind of hard to figure out how that can work, especially when you operate in space-time where the speed of light is limited. And the way to solve this problem is basically by using entanglement. We are all entangled with each other, so we share one collective wave function, and that's updated in a collective way. So it represents the knowledge of all of the collective of observers, not just one observer. And this basically means that we here on Earth, we are in an island of entanglement, and everything outside is basically a superposition and kind of not really there. Like it's there when you go there, but you're just seeing a potential existence there. You're just seeing the sun as it was 8 minutes ago, and you don't know how it is right now. And this explains the cosmic microwave anomalies. I don't know if anyone have heard of them. They were a big thing starting 2004, and then 2014 that they sent out the Planck satellite to check if they're really there, or they're kind of from background contamination from Earth's atmosphere. And everyone was shocked that they were still there, but then it became uncomfortable to talk about it. And the one who discovered them, Max Tegmark, discovered like the quadrupole, that there are cold spots basically in the direction of the north and south pole of Earth, and the north and south pole of the orbit of Earth around the sun. He basically more or less left cosmology, or mostly focusing on AI stuff right now at the moment. So I think that was kind of an uncomfortable truth, and also like a 180 reversal from what he published in his books before. This is not like the main topic of my talk, so I'm just going over those points quickly. When you explain quantum mechanics by saying we are in all worlds that are indistinguishable at the moment, it's kind of a simple explanation, and it solves the problem how you can have entanglement. Basically, in each world, like it was on the slide before, in each world you see that the spins are orthogonal. So when you measure, it's not strange to find them being orthogonal. So there's no spooky thing going on, actually. It's all very natural. So, but anyway, this explanation is too simple because this way you can only explain a probability distribution that is like shaped like a mountain, but you need something wave-like. You can have that if you have space quanta, which are like spheres. And there's this idea, this analogy between black holes and elementary particles. But what you need is something that is a little bit like a black hole, like something that's proportional to mass or mass energy, actually, energy. And so it's bigger when the energy is bigger. And so you can have a sea of overlapping spheres, and you can construct a space out of that. And that has to be a complex number surface, and that oscillates. Like a complex number goes around the complex plane, the origin of the complex plane, and so it phases in and out of existence. So the real part of every space quanta is shrinking down to zero and then expanding again. And that does the following. It basically makes the probability to detect a particle among every pathway go up and down like a wave. So here, the probability might be zero when you measure here when it has reached zero, but on another pathway, it might not be zero. So that's how you can get a probability distribution. But something that I hadn't realized quite in the early days, and I had realized it a bit, but I didn't try to find ways to test it experimentally, is that this actually means that the Born rule is changed. This is the normal Born rule. You take the square of the complex number to get the probability. But here you take the square of the real component of this complex amplitude and double that, and that's your probabilities. That's quite different. And when you look into lasers, you look into them, you see this granular structure, which actually, when you look at them with your bare eye, it changes a lot because you move left and right. But when you use a camera that is stationary, you see that those granular structures are very, very stable. And basically, those are the spots where the wave function goes to, the real component of the wave function goes to zero, which in standard quantum mechanics doesn't happen. It's always, the absolute value is always the same. Yes, the complex number changes, but the absolute value is always the same. Okay, so next topic again. So this is all one overarching theory of quantum gravity, and quantum gravity is supposed to solve all problems. So it has to deal with all topics that exist in physics, basically.
Right, a unified theory. That's the only way. It's got to take everything on. I feel that.
Yeah, thank you. So there will be a lot of topics. I'm trying to focus on gravity, but so I will try to go quickly through these topics. Entropic expansion is basically, I agree with Newton that Newton was asked, if there's universal gravity, then why doesn't everything just collapse? And he said, well, if the universe is infinite, then there's no center of gravity, and then you cannot have the universe collapsing. And that's just such a simple logic. I just can't believe how Einstein could just disregard this logic, and all those people who came after him, like Friedman, they're all using math, which is basically just taking the Einstein field equation, which is only made for one object. You cannot even apply it on two objects. And they just take it, which is basically they take the equation of collapsing star becoming a black hole, just take that upside down and then pretend it's an expanding universe. And then you get the absurd result that the probability for the universe to be as flat as we observed, spatially flat, no spatial curvature, the probability of that would be 1 in 10 to the power of 62. So that's the flatness problem. And instead of taking that as disproving Einstein's theory, at least when it comes to the cosmology, in my opinion, it doesn't say anything about cosmology. Instead of taking that as a disproof, they just invent inflation theory and try to solve it. So instead of, when a theory is disproven, instead of accepting that, they just invent some new stuff like dark matter, dark energy, inflation, all this kind of stuff. What I do here is I accept that it cannot collapse, and then I ask, okay, so why is it expanding? Like when you think it can collapse, then you can just think, oh, maybe it can't bounce back or something like that. So why is it expanding? So I'm saying it's expanding because of entropy, and it's in particular the entropy of black holes. So at the beginning, I didn't quite realize, okay, the entropy is actually a quadratic function. If you feed the black hole linearly, it grows like a quadratic function. At the beginning, I was thinking, oh, maybe the black holes are growing faster or something. And I look, okay, they were quasars first. But then I realized, oh, wait a moment, it's the surface, the entropy depends on the surface area. So it's a quadratic function. So if the expansion of the universe is in order to keep the entropy density constant, then if it depends on entropy is like a quadratic function. So that makes sense. And it's already kind of in Penrose's book. You see how he describes how the entropy changes, and he kind of alludes that it's constant in the middle, but then he still believes in Big Bang theory and all of that stuff. So he doesn't take his own diagram seriously. If he would stare into it and like meditate on it, maybe he would have this idea. But it's unlikely because he's very keen on Einstein's theory being the correct one and there being something wrong with quantum theory rather. Okay, then something not so important, but mathematically kind of impressive a little bit. I solved the hierarchy problem, like calculating how much of these vacuum fluctuations are there already in empty space. And the more you have of them, the weaker is gravity, because gravity basically depends on where there are more space quanta. So if you have a lot of space quanta here, then things are attracted to that place. So all of space is made of these vacuum fluctuations, and so every particle has a lot of gauge bosons coming out of it. So that increases the density of space quanta here. So everything gets attracted to it geometrically. So it's still, I'm not using curved space, but I'm using granular space. But it's still similar to Einstein's theory in that regard, because you have, instead of curvature, you have different densities of space. And if you already have an awful amount, crazy amount of these space quanta here, and you add one particle there, one charge, I guess you like the idea that charge is the thing that is important, not mass. So you have one charge here or one hypercharge, and in my theory, it turns out that hypercharges are more important. It doesn't do all that much because you already have this huge sea of virtual particles. And so that explains why gravity is so incredibly weak. Okay, now here again, back to cosmology. I checked it predicts, this theory predicts that the universe started off very slow and then became faster and faster, like a quadratic function. And it predicts that the true age of the universe is 42 trillion years. And I tested that by looking at all the supernova that exists. And it shows that the luminosity decreases with the square of the distance, as one would think, if the distances are correct, but in Einstein's theory, they're not correct. So on the left side, you see my theory. On the right side, you see Einstein's theory. You see my theory matches, his theory doesn't match. But in general relativity, it will match for distances for redshift smaller than 0.2. That's because in Einstein's theory, basically, they're using two different formula for redshift, smaller than 0.2 and another one for bigger. So this analysis basically shows that it can only be one equation, it cannot be two equations. In Einstein's theory, actually, it's many more equations if you go to even higher redshifts, which haven't been observed yet because they're too far away, except of course for the cosmic microwave background, which is the maximal redshift. So this analysis only shows that it cannot be two equations, it has to be one. But a way of furthermore confirming my distances is to look at the average luminosity of supernova, and that's, in my theory, it's very close to the predicted, theoretically expected value, whereas in Einstein's theory, it's not. And it's actually well known, people know that, or at least some people know, that there's huge problems with supernovae. They're too faint, the very distant supernovae are too faint for the distance they're supposed to be. And people have resolved that problem a little bit with dark energy, making the universe go faster. And I agree with that part. But the way they're doing it is not really solving the problem. It's just making the problem a bit smaller. But since 2019, there's this Hubble tension, and it's even all over the newspaper saying that cosmology doesn't add up. And people, physicists I talked to, other physicists, they basically say they left cosmology, or they're not interested in cosmology anymore because it's such a mess. Okay. Yeah, sorry to jump between topics so much. Quantum eraser experiments. They basically, you can use a quantum eraser experiment to prove that actually it's consciousness that collapsed the wave function. You can do that by erasing the Witch path information after the detector screen has been hit, and then the erasing is still possible, which proves that it's not the screen collapsing the wave function. And then you can even use that. You can look how long you can delay the erasing of the Witch path information, and then you can figure out when exactly the wave function collapsed. That's how you can, and I published that also as a paper in 2018. So, but it's very hard to delay it by a lot of time, because light is so fast. You would have to slow it down somehow using a Bose-Einstein condensate. Yeah, so here now I have to explain how Einstein's the things that are confirmed within Einstein's theory, how they work, because there are things you cannot deny, like time dilation. So basically, the way you get speed-dependent time dilation in SPD quantum gravity is you say, okay, when the size of particles of space quanta depends on the energy. So if you have a spaceship and all this space quanta in the spaceship are inflated, inside the spaceship you will not notice it, but it will manifest. It's like changing constants. If you make the space quanta bigger, I mean, they have a bunch of constants in the formula for space quanta radius. There's the speed of light and everything. And if you change any of the constants, g, well, g is not really a constant, but okay, you could, we'll come to that later, that g is not a constant. But you can change any of the fundamental constants like c or h and so on. Well, it's 3 of them. And it will always result in time dilation. So that's how you can explain time dilation dependent on speed. And dependent on gravity, basically what you do is you're here on Earth, and you have how weak gravity is depends on how much quantum vacuum, how many of these space bubbles are there. And on Earth, you have the background from the quantum vacuum plus the background from all the gauge bosons that are streaming out of Earth, because there are a lot of charges and hypercharges inside Earth, all the particles that make up Earth. So on Earth, gravity is weaker than in outer space. But you cannot notice it because it's uniformly weaker. Like in your frame of reference, it's weaker everywhere. So that's like changing constant. So that results in time dilation again. And it's important to notice that there's a maximal time dilation for gravity. If the escape velocity becomes the speed of light, like for a black hole, that's where you'll reach the limit. You can never go beyond that. That's why a star can never collapse further than the Schwarzschild radius. It can never actually become a true black hole. It will always be right before becoming that. So it's a star frozen in time. So you could also call it an eternally collapsing object. Yeah. By the way, I'm looking at my PPT, so I'm not seeing you here. Cannot look at both at the same time. Hope that doesn't matter. Okay, so that's what I said just now in the last slide. Yeah. Particles can come infinitely close to the speed of light, but they can never reach it. Escape velocities can come infinitely close to the speed of light, but they can never reach it. Hawking radiation doesn't exist because if you have gravity depending on the number of charges or hypercharges, then well, photons don't have hypercharges or charges. They're just photons. They don't have they don't consist of quarks or protons, neutrons. So a photon cannot carry away gravity. That's why black holes cannot evaporate. And I mean, if black holes could evaporate, that would violate baryon number conservation, lepton number conservation, because you have everything turned into light. Also, the second law of thermodynamics is violated. Well, people would try to convince you that the second law of thermodynamics is not violated by saying, well, the Hawking radiation goes into random directions, but that doesn't really help, because if it becomes a sea of photons, you can measure those photons and you know where they are and what their color is and everything, the frequency. So that's not like a black hole where you cannot see inside. So the entropy certainly would certainly be violated. The second law of thermodynamics would certainly be violated. But people only focus on information conservation, only 1 point out of 4. Okay, so now let's get to the gravity part of it, which is the main part. Now I already lost a half hour talking about the other parts, but all the rest now will be gravity. So here's the main calculation that you need. You want to, if gravity only depends on the number of particles, on the number of protons and neutrons, and this is something that should be interesting also due to electric universe people, which I'm not one of them, but depending on the intricacies of the theory.
I see the same slide.
Yeah, do you need me to switch to this one with the different slides?
Wait a moment, I was talking and I was switching slides all the time. You were not switching? It was not switching here?
No, it was not switching under this one.
So my whole talk is wasted then.
We were following for the most part. We just didn't have the slides. So
out of the slides. So how can I switch this? I was switching my own slides here. I thought you were seeing that. I thought it's a screen share.
It is,
it's not a screen share.
It's just showing the first one consistently.
Oh no, that's terrible. So
maybe try this one.
But I'm sharing the screen. Okay, so only you can switch the slides.
I think you should be able to. Are these the slides though?
Okay, yeah, I'm able to switch the slides. Yeah, but we are half hour in and now. Okay, let's just go through it.
That's
quickly.
okay. Don't worry about it. It happens. You just kind of go over some of the stuff. You know.
Okay. Just quickly here you see the picture of the spins.
Sky, there's no time limit, so just take your time and tell us what you want to tell. You know, no pressure.
I would just go through the pictures so that you have seen the pictures. Here you see the spins that are orthogonal on each of the indistinguishable worlds. Here you see the phase space, how we turn a point in phase space into a cloud. Okay, next one. Here you see the no alien prediction, basically that we are all connected through entanglement. And yeah, that's that. And then here you can see the quadrupole, that there's those cold spots that Max Tegmark discovered, and they are aligned with the equinox and ecliptic of Earth. So here you can see concentric circles here, but they're actually a bit more explained by baryon acoustic oscillation. But here you can still see a north-south asymmetry, so that's connected to that as well. Okay, and here you can see a straight line. It looks like a straight line, but when you zoom in, you see that there are these space quanta, and so it's not really straight. And when you have more space quanta here as opposed to there, then basically you have gravity, you get attraction there, and here you have fractional dimensionality, so it's not 3-dimensional, it's 2.99999, and you have 35 nines there, and that's why gravity is so weak. And here you can see a photo I took of a laser. It toned down the luminosity for it to be more clearly visible. And so this is the Yeah, changing the Born rule. Sounds kind of cool, like the Born identity. Well, but Max Born was a famous German physicist who later
No, I
became.
can't hear you anymore.
You can't hear me? Can you hear me?
No, I can hear you just fine.
Okay. So I will go on.
I could hear you.
Okay, cool.
Yeah, we can hear you, Philip. It's got to be on your end.
Yeah. Okay, so I will just go on.
US,
Yeah, so here
US.
you see it's only the real component of the complex number, so it turns to zero, the probability every time the real component is reaching zero. Here you can see the entropic expansion. You can see how the black holes grow and then the density goes down. So that's why the universe is expanding, and it's expanding like a quadratic function. It's not like in the mainstream where it's starting off 17 times faster than now, then slowing down and then speeding up again. It's very complicated in the mainstream, and the data just doesn't show that kind of complication. Here again, the hierarchy problem. Yeah, there's nothing much to see. I already explained it. And here you can see the data. You can see here how the inverse square law of luminosity. So here you can see it goes up. Luminosity actually goes down, but this is the magnitude, and magnitude is an inverse square logarithmic measure for luminosity. That's why it goes up instead of down. Here's the quantum eraser experiment. You can delay it more and more to see how when the wave function actually collapses. Here, yes, this is time dilation. Just some illustration here. I already explained this. Yeah, meme about it. Yeah, Hawking radiation. Okay, now we get to the gist, the gravity part. So if gravity depends on the number of particles, which actually should also be the case in all those theories, electric universe theories, which mostly are not very mathematical, and I don't really agree with them, but they should expect some similar results depending on how they count the neutron. Some electric universe proponents, they deny quarks, but then they would have to count the neutron as zero. So that wouldn't work. It wouldn't be supported by the data. But if they use quarks, then they could use an electric universe theory and still get close to the pretty close to the actual data in the experiments. So if you want to cut, you have the gravitational constant of iron, and the official gravitational constant was measured with stainless steel, which is close to iron. You take that number, and which for stainless steel is actually not 6.6743, but 6.6742 if you use stainless steel. So then you take that number and you can extrapolate how the gravitational constant should be for hydrogen, which doesn't have all the binding energy. So binding energy does the following. It is negative energy, and because mass equals energy, it reduces the mass, but it doesn't reduce the number of particles. So you have more particles per kilogram mass or per gram mass. So, but for hydrogen, it's not like that. There's no binding energy, so you don't have so much gravity per. So you can calculate out all this constant for hydrogen. Here, I don't know if you see my mouse. Can you see my mouse in the screen share?
No, it's because it's preloaded.
Okay, yeah, it's preloaded. Okay, with mouse it would be better, but it doesn't matter. Okay, so you can see iron inertial mass. You just take the atomic mass of all the different isotopes, and you multiply them with the percentages. How many percent of this isotope? How many percent of that isotope? So in this case, it's iron. So we're calculating out all the binding energy for iron. So then we get the sum for the inertial mass. That's basically the mass that everybody knows about. Gravitational mass, nobody knows about it. Gravitational mass is what you would get if you just naively add up all the protons and neutrons together and look at the result. So I did that, but for all the isotopes, you have 26 protons, 28 neutrons, then 30 neutrons, 31 neutrons, 32 neutrons. So that's the result you get. And then you divide the top by the bottom one. the inertial mass through the gravitational mass. And well, gravitational mass is just a name; it's not really a mass. But in this context, it makes sense to write it down like that. And you multiply that with the ratio with the gravitational constant of iron, and then you get the gravitational constant of hydrogen. So that you can use as a basis to calculate the gravitational constant of all elements. So the next where do I click here? The next slide. So here you have lead, and just now I also did an experiment, free fall experiment with lead. So here you just divide the opposite way around. You divide the bottom number by the top number and multiply that with the gravitational constant of hydrogen. So then you get back up again. You calculate how it looks like when you go to the bottom to hydrogen, and then you calculate how you get back up to some other element. And then for molecules, you need to be careful how you're doing it. You shouldn't mess it up. So you should, for the inertial mass, you have to separately, you 2 times hydrogen and then 1 time oxygen. Has to be clean. You shouldn't be using some average or something. Average would be wrong. It has to be this kind of sum. You shouldn't be using some average G values. Like at the beginning, I was doing it like that, and that's totally wrong. So this is a mixed materials. You don't need to look at the numbers. You just need to know the percentages need to be atomic mass, atomic percentages, not mass percentages. You need to know how many percent this atom, how many percent that atom, not by mass, because some atoms are very heavy, so they will be a very tiny mass percentage, but maybe a very big percentage in terms of atoms. Okay, now this is the most important part of the whole talk. These are all the experiments that exist, all the measurements of the gravitational constant over the last 50 years. So you would think it would be better to include the last 200 years, but actually no, because the initial experiments were not precise enough. They were very messy. So they're good enough. The experiments are good enough since about 1969. Experiments done by Rose and Taylor and some others. So those are the good experiments, and then you can see also here Hale did experiments that were before that time, but they were all already good. So that he was the one of the only ones who did different materials that cited for his equivalence principle, and because of the design of that experiment, it's designed in a way that makes these differences almost infinitely small. Like instead of 1,000th, it becomes like a millionth or something. But that's at the end of the talk, that part. So he just disregarded that then later, and then he just used one material. And the same happened to Ponticus from France in 1971. He used different materials. But he didn't do that Edwish experiment to convince him. He was already. It was what he did is he just took all the numbers, ran them through a computer, and they did some data homogenization that they do in climate chunk science a lot, yeah, then he just got equal numbers or similar numbers. So that's kind of fraud, I would say. And then he just left physics altogether and went into climate science, where this kind of behavior is sort of more acceptable. And then in recent years, they have all been using stainless steel because that allows them to agree with each other more. Yeah. So something that I didn't do before last year is I was only looking at the source mass, not the test mass. And that way I only had very few materials, like 10 different materials. And the statistical significance was not that great. But then when I realized, okay, it was a big thinking mistake to not use both the source and the test mass. But then when Yeah. So it has to be the geometric mean between the source mass and the test mass. And so when you add all these experiments together, then the chance that this is a coincidence is 1 in 10 to the power of 13. Now, in my other presentations for APAC, I claimed some crazily bigger number, like or smaller number, depends on how you look at it. This is the correct one. The other one was wrong. But I had to figure out how to calculate the hierarchy, how the chances to observe such a hierarchy by coincidence, and it was not easy to calculate. I had to figure out how to calculate that. This information was not available anywhere, and still haven't seen it anywhere. But my method should be correct. Okay, next slide. I did some. Okay, one more thing I need to say about the last slide. So this is all assuming that the mass has been measured. The masses have been measured using a true balance, a mechanical balance, and all the legit experiments must have been using a mechanical balance, and they are very precise ones. I mean, in the old days, they produced a lot of mechanical balances that had could measure 4 digits after the decimal point in gram, and I bought one of those over there, but it's broken. All those old balances are broken, and then I have a newer one here. Measures 3 digits after the decimal, 2 or 3. So yeah, they have been using mechanical balance. In my own Cavendish experiment, I was not using that, and I was not really measuring precise enough to really use that value for anything. But I did a good effort, and I did better than all the YouTube videos on YouTube where people try to do the Cavendish experiments and they all fail. Like they don't isolate for air enough. There was a teacher trying to do the experiment for 2 or 3 years, and he never isolated from air, so it always failed. And at the end, he had to give up. So basically, I put it into a big container and put glass over it. And even then, I got 1 order of magnitude too big of a big G value. And then I figured out, okay, I have to put the tape around it better. I have to fold it over. Before I put the tape in, I didn't know I have to fold it over. I didn't know it was that sensitive. Then I had to move it out temporarily because I was doing it in a factory, and they had to use the space. It's a family factory. And then outside it, I realized, okay, it's totally not isolated from air. So once I folded over, it was working well. But still, I rely on the measurements that are already out there, not on my own. So this was fun, but I'm not relying on it. And then I also did some, before that, I did some Bernoulli trials, which was not air isolated, but just looking at statistically, if you have iron and water, which one will it be quicker? And I don't know if it was magnetism or a little bit of psychokinesis or what, but I was measuring the mass using a normal electrical balance, and that's just dependent on gravity. So that's not very usable here. Yeah. Differences in free fall. So it's not obvious that free fall acceleration should then also be different, but it's obvious when you look at the Newtonian equation. Where's the Newtonian version? Do I have put it here too? No, it doesn't seem so. But anyway, so you look at the first equation here. Instead of big mass multiplied by small mass, I have big Y multiplied by small y. And that's the quark count. But you can replace it by baryon count, proton-neutron count. Doesn't matter. Then this constant will be a different constant, but that's not the main point here. The point is that when you try to calculate free fall acceleration, you move over the mass here, you put it down there, and in Newton's theory, the small mass would cancel out because there would be the small mass on the numerator and the denominator, the numerator and the denominator. So then they would cancel out, but here they don't cancel out. So you get a fixed ratio between this y and this m, And that fixed ratio tells you that for every chemical composition, you have a different free fall acceleration. And the more, let me check on my screen because it's so small here. Yeah, okay. So I don't know if you can see this well, but the second line here, it's in white, so it's not so easily visible. You can see here it's formulated only using mass. You have the big mass, the small mass, but you have these G values that are different for each element. So so here you can let the small m cancel out. It's no problem because the chemical composition of the small m, it's still here represented in the G value of the small m. Mass cancel out, doesn't matter. It's still there in the chemical composition is still maintained. And so this second formula is the practical one that we use in everyday life in calculations and predictions. The first one, you cannot directly observe the quark count, so it's more for the theoretical work, not so much for the practical. Yeah. So then there's the SAS drop tower experiment. There's also video of that available. You can see it on the website of SAS, but he passed away 2 years ago, and his website went down just a few days ago, I think. I don't know if it's back up, if it's a glitch. His son is managing his website. He did a free fall experiment in the Bremen drop tower, and it totally disproved Einstein's theory, but well, they only let him drop it one time because they didn't like his conclusion at all. They were horrified by his conclusion, so they didn't let him try again. And then he even went in front of the courts, and he became very bitter. His whole website was ranting against the establishment, basically, for not letting him try to do it again. And the way they let him do it was also not so perfect because they only let people drop things inside their aluminum container, and then they stick to the ground. And especially when you make a vacuum, then something can get stuck on the ground. Really, this is like a vacuum welding. And actually, two masses got stuck on the ground, beryllium and boron. So that's why the experiment is not perfect. Only aluminum and iron should have stuck to the ground, and they did stuck to the ground because they've aluminum falls as fast as the aluminum container, and iron falls even faster, so it sticks to the ground. But you can still do some analysis of the experiment. How far did they move up, and so on. But it's just one single drop, and you cannot have standard deviations, and it's not really very scientific when you have only one single trial, and to use that is not very legit. And the p-value is not very impressive. It's just 1 in 30 chance that it's a coincidence. But while you have to take this p-value with a grain of salt, because I mean, they shouldn't have lifted off the ground at all. So you could say maybe it was shaky, and that's why they got a nudge and they moved up. But it's disproven by the fact that carbon actually got stuck for a moment and then lifted off the ground in mid-air, where nothing can hit this capsule. Okay. Next slide. This is much more impressive, but sorry, there's no picture here, and it's not something that you can have a picture of. I guess you can have a picture of the experimental apparatus, but this is a these are neutrino free fall interferometer experiments, and I don't know, is it every single one of them? But yeah, pretty much every one of them has neutrons falling slower than other objects, and that's exactly what my theory predicts. 1% slower. And on average, that's exactly what happens. It's exactly 1% slower. And yeah, neutrinos fall the slowest of all things that exist in the world. Neutrinos have the least gravity per kilogram. They're a little bit heavier than protons, so that's why the gravity per kilogram is the smallest. And these are my own free fall experiments back then, and was using this. Where is it? Using this thing here. Yeah, this was release class elements that are I could use iron, and lead is also still fine. Lead is a little bit conductive, but most other materials I couldn't use. And it's with the receptor platform, so the values can only be too large, not too small, because there can be a delay in the release, a tinier delay. That's why for those experiments you have to actually use the minimal delay, the minimal free fall time, not the average. You cannot use the average in this case, which makes it less scientific because people like to use the average. So that's just the first version of the experiment that was back in Greece. And yeah, the predicted difference at that height, it was like very, very tiny. For 2 meters, it's 0.3 milliseconds, like 0.0003 seconds. Then later I switched to using photogates, using lasers, but still with that clamp. And that's much better. You get very much smaller. Well, the standard deviations don't change that much, but it's more scientific. And also the receptor platform doesn't always react, but the lasers, they always react. And unless you miss them, then you have to readjust the position. Then later I used the magnetic release mechanism with the receptor platform. That was nice. It's a very clean release, so that makes the standard deviations much, much smaller. But then there's a downside to that. Then the size of the washers that you use for the magnet are become very important. So you use vending machine balls, and then you put the material like iron and lead, you put them inside, close it again. And the mistake that I was doing back then is to have different balls, one filled with one material, one filled with the other, the right way. And it was nice because I could alternate between them, one time this material, then the other, between each trial. And the mistake in that is because the washer size is slightly different, so that can introduce a bias. So the right way to do it is to use only one ball and then to just swap the inside. The reason I was not doing that or didn't even think about that is because at that time my vending machine balls were breaking open all the time, and I had to actually glue them to keep them closed. And now what I'm doing is I have a lot of pillows, a lot of towels. Actually, I put there like 10 different ones. Yeah, so it's very soft, and it doesn't even jump up at all, and they cannot break. And also it cannot hit the photogate. It was hitting the photogate all the time and was switching its position, making everything messy. Now nothing is messy. Not nothing, but these problems have been solved. So there was a bit of bias there. Then sometimes I would wrap them in paper because I didn't want laser light to pass through, because then the laser cover time, if you measure speed, for example, then the cover time is very important because you're passing only through one laser. And if it's filled only a little bit, then it will become transparent very quickly. And then the cover time is different, changing your assessment of the speed. But if you have two laser gates, it passes through the first one and the second one. So it counts the time from when the first laser got uncovered, when the first laser got covered, and then when the second laser got covered. But then it really doesn't matter when the uncovering is. When you look at only the time between coverings or uncoverings, then it doesn't matter that it's transparent. And I also, through trial and error, I also found that it really doesn't matter. So for some time I was wrapping them in paper and tape, but I abolished that later because it didn't seem to be important. Only it's important if you want to double check the initial velocity, for example, to see if there's any repulsion from the magnetic release mechanism. But that doesn't play a role anymore when you use the same ball for both. Then you have the same washer for both, and you don't have to worry that the washer size is a little bit different. Yeah, with zinc trials, 0.5 milliseconds. Okay. Yeah, now we go to pendulum experiments. I didn't conduct them. Giorgio Toro did. He's an American who moved to Italy, and yeah, he has this Italian name. So he did this pendulum experiments in a real vacuum. And actually, my free fall experiments, they would also be better in a real vacuum, and I plan to do that because I mean there's so many factors. Elasticity even could play a role. The inside, the whole dynamics. So vacuum is much better. So he did them in a vacuum, and the first experiment for 2023 got the perfect hierarchy. All of the 4 elements that he used lined up perfectly, exactly as I predicted. So the chance for that is 1 divided by n factorial, so 4 factorial. So it's 24. So it's 1 in 24 chance that this is a coincidence. If you just look at the hierarchy, so here you can see easily how hierarchy works. When the hierarchy is perfect, it's very easy to calculate what the chances for the hierarchy. Just 1 in the number of configurations that you have. If you have 4 elements, it's 24. If the hierarchy is not perfect, then it gets very complicated. And it took me some time of, I was thinking very deeply about this mathematics for 3 days until I figured it out. Okay, but I don't show it in this presentation. It's in the papers. In the paper. So he did this experiment again with more elements. The hierarchy was not quite perfect, almost perfect. 1 element was out of line, but still, if you combine the 2, you get very low chance that is a coincidence. What is it here? 1 in 1,791. My turn off my background sound while I have this mic. Should be good enough, unless it's not well connected. If it's not well connected, I cannot do anything about it. It's too late, I guess. Or should I check the mic? No. Yeah, I should be using the right microphone. Okay, anyway.
Yeah.
Well,
we hear you just fine.
Okay, so balanced scale experiments, they have been quite a ride. In the old days, actually not so long ago, I was really believing this myth is because they have the name balance in the name. So the reason why they call them balance is because they have this force resistance. So in a real balance, you have gravity actually providing that balance in force. But if you don't have that, then it really doesn't know how much electricity it needs to apply. So so you really need to use a mechanical balance, and you can look at anywhere an electronic balance. It's really just more precise. That's why they call it balance. It's not really a balance, and you still needed to calibrate it for different elevations, for different local gravities. So that's not something that you have to do for a real balance, a mechanical balance. And yeah, there are very precise mechanical balance, but they're not so much available in the private sector. So my early experiments on that, they were not good. I was just for the very small. If you have these element cubes, I have all these different elements, 50 different chemical elements here. You can buy them at luciteria.com. Basically, when you have a very small mass, then you measure a couple of times, and and the value can pretty much land anywhere if you compare the reading of a scale and a balance. Well, what I had back then, it was not really a scale of a balance. It was both a scale and a scale, a cheap one and an expensive one. So it was not the real deal. And the real deal I'm only doing since 1 day, so there are not many results. I posted one quick result yesterday on Facebook, but it's not ready yet, so I'm not going to talk much about that. But that's for the technology to build a material analyzer for you can use gravity to analyze a material. You can basically, in China sometimes they sell fake gold bars, and there's just some other metal inside, and only on the surface there's gold. So if you use a machine for material analysis, that's not it. Just to demonstrate. So they just can measure the light from the surface. So then they will think, okay, it's real gold. And if the weight is right, they can easily fake the weight by using other materials to achieve the same weight or mass. So yeah, that's something you could solve with this technology. And initially I thought I need a gravimeter to measure force very precisely. I didn't know that a normal analytical balance is already measuring force very precisely. I thought that just because it's using this force restoration mechanism, that it's not measuring force, that it's measuring mass, but no, it's measuring force. To measure mass, you really need to have this mechanical device, which is kind of cool because we moved so far away from mechanical things. Yeah. Yeah, so this is an example for classical, which actually has the right accuracy for my application, but it's broken, and they sell many of these online, but they're all broken. There was one which was not broken. It's actually the one in the picture, but I wanted to buy it, and I paid for it. But then the one trying to sell it to me, he slipped up in the stairway, and it just fell down and got broken. So that's that. And okay, here we go to some science fiction part, which is not fiction, but it's very difficult. So I guess it's if you were able to inflate mass, and some people they can do that. I think they can do that, but just playing okay, that's crazy. You cannot do that because E equals mc squared. You just need so much energy to change mass significantly for it to be measurable. You can see it for particles, but for big objects, nobody can do that. So one would have to be able to do that to manipulate gravity on a large scale. You could use fiber wires and fill them with some very dense gas like xenon gas and accelerate them using lasers. But you cannot just use the laser to push it. You have to actually use a laser pulse. You have to pulse it, and you have to do it in a very sophisticated way. And people have done that with air, but of course air is not heavy enough. And your laser have to be lighter than the whole thing. You need to actually make the gas inside heavier than the whole thing, your whole machine basically. It's very difficult to do. You can basically just have this loop and a small laser, but if it's very small, maybe it doesn't have enough power to do that. So yeah, it's very tricky, but theoretically possible. And then when you are in Earth orbit and you do that, your spacecraft falls slower than the people inside. They're falling around Earth, then basically they get pressed against the ground. That's how it would work. So you could have Star Trek Enterprise level artificial gravity, but yeah, very, very difficult to do. And yeah, maybe it's very hard. Okay, next slide. Yeah, I like Star Trek a lot, but yeah, warp drive is not possible unless you could make the vacuum energy around the spacecraft very low. Then you could do it, but there's no way of doing that. I don't know how you could do that. Maybe no, I mean you have to use the Casimir effect, but there's no way of having the Casimir effect everywhere around your spacecraft. Maybe by ionizing everything around you, then maybe yes. I don't know. Maybe that would polarize the vacuum in a way that would lower the density, maybe. But yeah, that's very okay. Okay, so here we have evidence from astrophysics, from cosmology. So the Earth is heavier than we think because the gravitational constant of the elements that Earth consists of are much lower than the gravity of iron. So you need more mass to achieve the same gravity as Earth has. So it's 0 point something. I forgot the exact figure. Heavier is 0.05 something. I don't know. But for the Sun, it's quite significant. For the Sun, it's 0.5% heavier. The Sun is 0.5% heavier. Quite significant. A black hole, neutron star and black holes, they're much heavier than we think. Their gravitational their gravitational constants are much. Sorry. They are much lighter than we think because their gravitational constants are not. The Earth's gravitational constant is smaller, but black holes and neutron stars, their gravitational constants are much bigger because they have all these gravitational binding energy reducing the mass but not reducing the number of particles, so they have huge amounts of gravity. So neutron stars have 15 to 20% nuclear gravitational binding energy, and black holes have 30%. So they are much lighter than we think because their gravity is so enormous that they need much less gravity to much less mass to achieve the same amount of gravity. So that solves the mass gap between neutron stars and black holes. They both get lighter but in different amounts, and that brings them together, and there's no mass gap anymore. So this mysterious statistical gap that you have between them, which is huge, it's like a whole solar mass or something. Yeah. So that's gone then. Not quite a whole solar mass, but close there. Okay. What's this? Yeah, you get. Yeah, this is the same. Just the math of it. Yeah, the mass gap shrinks down from almost 1 solar mass, 0.95 masses, to 0.3, which is the statistical gap. It's just a normal statistical gap. And you also get close to the Tolman-Oppenheimer-Volkoff limit, which is telling you what's the maximal mass of a when a white dwarf cannot be a white dwarf anymore, has to become when a star cannot become a white dwarf anymore, but has to become a neutron star. And there's a big disagreement between theory and observation, but in my theory, there's no gaps like that. And now to some more spectacular stuff, or maybe equally, but more popular stuff. I mean, everyone talks about how Einstein's theory solves the perihelion precession of Mercury. Well, my theory does it much better. For Einstein, his accuracy is like the standard to look at is like Duncombe, 1956. That's 99.89%. For me, it's 99.98%. Yeah, and overall for him, it's on the average, it's 64%, 99.60, 74, and for me, it's 99.90 for the average of all. But actually, only the last one is important because those are not such good measurements. Duncombe, it should be the same. It's funny that they have the same name. Oh well, there's a small typo. It should be Duncombe with an E at the end. I guess it's French. The E is silent. And that's where I was in 2024. But the figures I have here, I was updating my slides. The figures here are actually from 2025, because here I was using the correct distances between the planets, because when you have non-Newtonian gravity, the distance of the planets are also changing. So these results are more accurate than the ones I had in 2024. So I should write 2025 here. Next slide is the perihelion precession of all the planets. This is a big, very amazing, at least I think so, amazing breakthrough this year. Before, I didn't bother to calculate them because I thought, okay, perihelion precession in my theory should always be smaller than what we observed. But that was not the data. It was showing it sometimes bigger and sometimes smaller. And using my original method of calculation, it suggested it should always be smaller, because back then I hadn't calculated what the interplanetary distances should be. When you account for that, then you get the correct results. And I beat Einstein's theory for all the planets. You see that my accuracy is higher for all of them. And agreement, we both have agreement for all of them except for Mercury. Einstein doesn't have agreement for Mercury anymore, which is quite shocking. And it wasn't clear until 2017, because you have to really calculate for the expected theoretical prediction for Mercury. It's so sensitive. You have to calculate in all the planets, not only all the planets, but also all the comets and everything. When you do that, you get a value that's a bit too high, and that's why Einstein's theory doesn't agree anymore. And that's something you don't notice right away, because only since 2017, Park calculated that, and it was a bit too much perihelion precession. Yeah, it was too much for me. I predict the right one. Okay, next slide. Here, many people only show the anomalous precession, so that's actually very bad. They always show only the precession that's relativistic and not the full precession. For the outer planets, for example, nobody even reported the full precession. And so they only report the anomaly, that part which is not explained by Newton's theory. So because it's so popular to show that part, I show it here too. And it also shows that the difference in the agreement is much much different between my theory and Einstein's theory. So here you have 27% for Einstein, and here 73. Okay. Okay, next one. For Saturn and Jupiter, it's very hard to have data. So there's only some reportings of only the anomalous precession, which is here in minus. So so it's very hard to judge, and those come from computer simulations, which are compared then to observations, and they get adjusted all the time. So all the anomalies get adjusted away by basically rearranging all the planets, changing the distances up. It's basically just always remixing, because they always have to use computer models that are Newtonian, so they cannot deal with any anomalies. They just adjust away every anomaly. So this reported anomaly for Saturn, it got tuned down in different publications and made smaller and smaller without even explaining what happened there, why it's gone suddenly. And the one Ioria, what's his name? He's looking at he's testing basically non-Newtonian theories, and he's just saying, okay, if Newtonian gravity is not true here at this distance, then for that distance the discrepancy should be even bigger and bigger and bigger. So he doesn't even think of theories that are composition dependent. So that's not really testing Newtonian gravity. Is not really a test. Here also test for gravitational waves, orbit decay, very famous. The Taylor pulsars, they get closer and closer because they're losing energy due to gravitational waves. If you use my theory, you can calculate that much more precise, and their calculation is not true and is not agreeing anymore since 2010. The Taylor pulsars are not agreeing with general relativity anymore, but they agree with my theory. But there's some ambiguity about them being, are they neutron star pulsars or are they white dwarf pulsars? And in recent years, it's become more popular to think about white dwarf pulsars. So some of the pulsars can be white dwarf, some are neutron star pulsars. Okay, this is almost the last slide, one before the last slide. Okay, how many people are still there? 2 people, 3?
We still here?
I'm still here.
So
We're all still here.
Experiment, and here you have a beam, and it's basically comparing the centrifugal force induced by the rotation of the Earth with the gravity. So, but because they're on the same beam, that's why you had the different materials. They kind of they share the same gravitational acceleration, basically the same small g value, and that's the only reason why any difference at all was measured, is because one side was suspended and it was at a lower potential. And that's why you have this tiny effect, and I calculate exactly how tiny the effect is. And the odds for this experiment is 1 in 400,000 about. Yeah, and this data is from 1922, and this is what Einstein cited for his equivalence principle. And he basically ignored all those differences because they are small, but actually the error bars are not overlapping. So actually it's kind of disproving the equivalence principle. And this was not noticed until Fishbach noticed it in 86, but he framed it as the fifth force. He's the one who popularized the term fifth force. Now we have the Kepler ratios in the solar system. Kepler, 1617. He basically showed that the ratio between the square of the orbit period and the cube of the distance is always a constant. But here I show that it's not a constant. and it follows the chemical composition of the planets pretty neatly. And when you use modern data, you have to actually split up the inner planets and the outer planets, because for the inner planets, they're basically using the measurement data a little bit, but then like 99% of it is just using the orbit period, and then from that getting the distance. So they're not using the real distance, but because they're using a little bit of real data in the mix, that's why you can still see the composition dependence a little bit there. Here, not so much, but we go over to these slides here, and you can see it very clearly for the outer planets. It's much more clear, and there you don't have to. For the inner planets, I had to basically magnify the zoom in on the graph basically by multiplying it with something, and that's how for Mercury it became the same. I basically multiply it by something that brings the values together for Mercury. For the outer planets, I didn't do anything. It's just the raw data. Well, on the inner planets, it's not raw data from the get-go. It's what they publish, and it's not raw data. So I just tried to extract the original pattern from the manipulated data. And then we have here Standish is very bad. P-value of over 50 means it's like negative. It's like an inverse hierarchy. And yeah, Arthur Cox also not very good, but NASA has the best one. Here you can see it follows the hierarchy pretty neatly, and the chance that this is a coincidence is 2%. So this is lower than for what was it for Kepler? For Kepler is okay. Actually, Kepler was even better. Kepler was 0.46% it's a coincidence, and NASA it's 2.2%. Okay, that's the last slide. Yeah, that's my presentation.
That was awesome.
Very good
51 slides, amazing.
Very nice. Thank you.
Listening.
Give him an applause. Come on.
Good call, Gerald. Absolutely. 51 slides.
Audio here.
I just finished.
I'm already the second person who doesn't have audio. At least you have audio and you were able to listen to me.
Absolutely.
And everyone in the chat as well.
I'll be honest, I'm not a physicist,
don't
but
know
I
what
enjoyed learning as
about
much
that.
as possible.
Okay, anyway, it's a pleasure. It was a pleasure
Nice.
talking here.
Thanks.
Let me check
Appreciate
the
it.
chat. Okay, anyway, it's a pleasure.
Nice.
Yeah.
Are we able to?
Yeah,
Well, I
really
guess
good.
we do the presentation.
Okay, anyway, it's a pleasure.
Nice.
Yeah.
Are we
Big
able
applause.
to-
That was really good presentation.
Yeah, thank you for your presentation. That was awesome.
Big applause. That was really good presentation.
Yeah, thank
That
you
was
for your
really,
presentation.
really good.
BDK, I gotta mute you. You have echo going on there. Sorry.
That's really cool. Each element has a different gravitational acceleration.
Say that again. Can anybody hear me? Yeah, I can hear you.
I can hear
Can
you.
you hear me? Okay. We had a little glitch.
Well,
The headset, okay.
Yeah, I had a delay for a second there. Is there a
Yeah,
delay?
so did I.
Yeah.
Maybe
you know,
that
it's
presentation
like
was a
Saturn.
little too hot.
Maybe.
It's like Saturn's rings.
Each element has
How
a
it's-
different relative gravitomagnetic permeability, so
Oh, no,
you're
he
gonna get attracted at different speed. I mean, at different acceleration. So
Okay, so
that's
I hear you
awesome.
now, so you have to start
I've
over
got a
again.
question for you, Sky. What do you think about the? What do you think, Sky, about the vacuum catastrophe?
Yeah, I solved the vacuum catastrophe. Basically, Newton solved it. Newton solved it because Newton said in a universe that it has no center of gravity, there is no gravity. And I mean, vacuum energy is evenly dispersed everywhere, so it shouldn't have gravity. Very good question. Yeah, if there's no center of gravity, there's no gravity. So something that is evenly distributed, only in Einstein's theory it would cause gravity. So the vacuum catastrophe depends on on Einstein's theory.
Am I
On Einstein's
correct?
cosmology.
Am I correct to say that your model gravity is more of an effect than a force, sort of thing, or is it still a force that's just dependent on the atomic mass density?
Well, I think we should just call things what they are computationally. I mean, in quantum theory, they say in quantum physics there are no forces. They say they're only probability distributions. Then they basically shift each other around with these gauge bosons. So there are no forces. And in Einstein's theory, it's geometrical. So they say there are no forces. It doesn't really make sense to just say there are no forces. I mean, the word force makes sense. It's in our everyday life, and I don't think it makes much sense to just say, "Oh, forces don't exist."
Fair. I like that.
Yeah, thanks.
How do you incorporate the spin vectors on the atomic scale? How does that affect, its direction, its spin? Because,
Yeah, so spin is very mysterious. You need like two revelations to have the same state, and that sort of thing that can be explained, I think, with when taking serious that particles are really these complex valued spheres. You have the real component shrink down to zero, then the imaginary component grows and it goes to negative. So it goes through all those four different phases, and so the rotation becomes more abstract. And I mean, complex surface spheres are basically what you use to describe spin. But for if you have bosons and not fermions, their spin is quite different, and for them also spin is more restricted. It has to always be in the direction in perpendicular to the direction of movement for a photon. So it's quite different from an electron. It can just spin in any direction, but for you can only measure it up and down, but it can be relative to any direction.
I absolutely love that. I love what you are saying right now.
So an analogy to that would be a cylinder magnet, end for end, north facing, say the roof, and it's spinning centrifugally, but it's still standing end for end. Is that correct?
Well, what I tried to finish there, I didn't quite finish, is I wanted to say that fermions would be two-dimensional complex number spheres, so 4 dimensions, but bosons are one complex dimension, so it's like a two-dimensional sphere. So that's why you have less degrees of freedom and it's more restricted.
All right. Thanks for the answer.
Welcome.
That's really cool. Awesome.
Thanks.
Philip, did you have any other questions, or? I guess for the last half hour or 40 minutes or whatever we're doing, maybe I'll just do a round table. Philip, you do, I guess, update on what you're up to. And Philip?
Phil?
Yo.
Can you hear us?
Tried the annihilation process and the pair production and all that, or you agree with the mainstream?
About pair production, has anyone noticed that no experiment on Earth has ever created a surplus of matter as opposed to antimatter? It's always
there's delay in. I can't hear properly, but there's delay in the stream.
Oh, there's delay.
No,
Oh,
hear
that's why
everything
he was just
fine.
sitting there for a minute.
No, it must
Well,
be Philip because
actually, there's something. Well, you know, in Germany, it's 4:30 now. So last night I went to bed very early, and I changed my sleeping times, which are very. I sleep very late normally. Last night I slept very early, so I want to kind of try to sleep early. So yeah, it's 4:30, so I should go to sleep now. So I will leave you now.
Well, thank you very much for your time.
Yeah,
Thanks
for
for inviting
presenting.
me. It was a pleasure.
Thank you.
Yeah.
Very good presentation.
I guess we'll just do like a round table. I guess.
I finished it up shortly before coming on here. I updated. Okay, bye bye.
Have a good sleep.
I've done that many times. Finished a presentation right before you go live,
Okay.
or as you're live.
Yeah, that was really cool. Yeah, I think Philip's got some lag going. I don't know. It's weird because I heard the whole stream, no problem whatsoever.
I heard it too. Yeah.
Yeah, I didn't
But
have any issues.
so, Gerald, what have you been up to?
Go 5'8". Just kidding.
Cheers.
The same height as me.
There you go. I'm short.
Ben is here.
Yeah,
Ben
Ben.
is here. Yes, I haven't seen Ben in a long time.
Can you hear me now?
He is? Where is he?
Yeah, we can hear you, Phil. Can you hear us?
Yeah, I'm probably the one being monitored by I'm the one being monitored by the CIA right now.
Oh,
Absolutely.
we all are. Don't
Bogging down
worry.
his
Why?
system.
Dude, I got
Well,
invited to something like in September. I told Phil about it. So tell me who's being monitored. You know, I was
We're all
invited
being
like
monitored. I mean,
man,
come
like
on.
no, but this is
Everyone.
this is like for national security kind of thing.
They're going to
It's
recruit
like
you because you're part of this, Lulu. Be careful.
well,
no, but this is cool. This is really cool. Like I have a place where they hear me. Like even if I don't like get to do anything, but okay, I'm outspoken. I like
Well,
tell
then, for
them
your
I don't
sake,
care.
for your sakes, I'll be nice tonight. Then
Huh?
I said, for your guys' sakes, I'll be nice tonight.
Thank you. I have to cross the American border in 4 days. So that
Right?
right.
You don't
So
want
we gotta
yeah, good luck with that.
behave. And I'm sad I was outside when
Behave.
Sky left, but that was
Whoa,
pretty
whoa, wait a
awesome.
second. You never said behave.
Well, class,
I'm just playing, guys.
classic Gerald, right? Classic Gerald.
Go ahead. I'll shut up now.
Classic Gerald, right? Classic Gerald. We have CBK Wahoo Chris with us. Chris, I believe you still have the YouTube going maybe in the background. There's like an echo whenever you're unmuted, sir. Chris, I believe.
You know, the
Yep.
previous
Continue.
speaker was
Sorry.
talking about. Can you guys hear me?
Yes, ma'am. Loud and clear.
Yep.
Okay, so the previous Sky, the presenter, was talking about like the gravity pull between Saturn and Jupiter. I did a simple search. I wanted once to kind of find a thread on what what causes like a stock to rise and go down. And from what he's been presenting, it's it's different, two different frequencies, that's still connected. But this is what I found. I found a paper that some shell scientist said that there's a connection between the gravity pull or the fluctuation difference between Saturn and Jupiter has a direct connection with the rise and the dips in their stock. And this is a paper I hope I could read, like either I emailed it to myself or PDF'd it, but usually, when I find these things, I try to like extract them just so I have a copy of it somewhere as proof, like this is real. And so when he was talking about the different, yeah, it affects everything from like a scale, you know, like on to the last element of even our composition. So yeah, there is the gravity affects you know, all the whole ladder of the scale. So, you know, just I wanted to add that, but you know, I think he was in a hurry.
Yeah, for sure. Because it's like a theory, like he said, and like there's a lot of parallels with what he was saying and my own of a theory of everything literally has to have the theory of containing everything. You have to unify everything within it, and a lot of it is geometry.
The only issue I have with everybody coming up with a theory for everything, where's the device that connects all these theories?
God.
Yes, of course. But well, I'll leave it at that for now, because we're gonna get into part of my presentation I don't want to get into. So
Oh, okay.
sorry. Future things. I'm working on something similar to what you're doing. So Bernie, you and I, we have to have a talk.
Yes, we do. Long overdue.
Did you guys recently or see Sabina Hassenfetter's video on gold from nuclear fusion?
I have yet to watch that, but I have been watching
rings a bell. I've
several
seen that
different
somewhere.
fusion
Yeah,
companies claiming that they've done lead to gold,
Yeah.
including CERN, but
That's
then a
right.
couple of other fusion startups now also claiming it.
I
There's
watched
a
it, but
bacteria. There's a bacteria that eats up heavy elements and it poops gold.
Yeah, you
Like
sent
I,
us that,
Nice.
Lulu.
I searched that. It's real. Like
I
there's
want
a
some of
whole
that bacteria.
Gold is
Yeah.
alive.
yeah,
Gold
but
grows.
like
Yeah, some people say that.
Yep.
Yeah.
As
you
an
know,
alchemist, I have to entertain that possibility of reality because that's how they
Did you
speak on
hear
it.
about
it-
that one company that states they can pull gold from Mercury just by
Yes,
beaming
I did.
neutrons at it?
okay, that's not the
Yep,
cool part. It's not the gold is not the cool part. The cool part it could like eat up all the bio waste, all the hazardous stuff. That's the cool part. There's you have this that could just make it go away, you know?
Well, that's part of the Atoms project that I've been working on. It
Yeah.
literally captures like nuclear fallout, pulls it in, pulls the energy out of it by running it through various loads, and then grounds whatever's left over. The particle that's been captured goes to its daughter product and its daughter product and its daughter product, and you can decide what you want it to be at the end. The
Yeah.
atoms,
Also,
that's what I call it.
Hutchison was
I love
Hutchison
that.
was working on Hutchison was working on some stuff back in the day where remember the big BP oil spill.
He figured out
And-
how to do it, but he figured out how
Right.
to transmute it and literally clean it. He couldn't
Yeah,
capture
that's
it and
exactly
then
what he.
turn it into what he wanted, right?
Yeah, he was using frequencies. He was basically
Yeah.
using ultrasonic frequencies and just blasting the water with it.
Yeah, his
So-
basis on it was interferometry. He was using two frequencies in their cross patterns.
Right.
Yeah.
Right. Yeah.
It's like how they could use it and if somebody has kidney stones and they don't want to like do any incisions, they use the two kind of frequencies to, you know, make it into like smaller bits. I mean that's
So
yeah.
I don't want to get Mike into trouble, so we'll call this the woo.
Yeah.
So here's a
sorry.
thought experiment, right? You guys have heard of the med bed? What if there was like a medical shower that you could stand in? Like a dry steam shower that literally had electromagnetic resonance that would, I don't know, maybe attach to certain issues in your body. And along with red light therapy and certain other flashes, in this thought experiment, perhaps your body's natural healing ability would turn on and things would just help themselves. Do you understand what I mean by that?
100%. And I like the sounds of it, and it sounds pretty similar to the Kesh plasma field technology. And
Yeah, this is a whole system that, yeah, it's very interesting. Something we can get into, definitely.
look forward to
I'm on
talking about that. We'll have to do maybe a rumble on the health side because stupid YouTube terms of
Yeah, well, Rumble's getting that way too, so it's kind of hard to gauge it. I mean, I got no strikes on my channel, and I'm not getting paid in any way. I don't have Patreon. I don't have subscribers or a club you could join. So who knows? Maybe what you'll see on my channel next. We'll see. I could afford a warning or two,
Very nice.
right?
I like.
Information to get out's more important than my freaking arse, if you know what I mean. It's just the way it is. Besides, with Canada trying to pass C63, if they do, I'm done. I'll be off internet at that point permanently. I'm not showing ID to prove who I am or my age just to get online. That's a load of crap, man. Online was not created for that purpose. So if you want to track me to go online, have a nice day.
The
You don't need to
internet was
track me down.
created to survive nuclear catastrophes.
Yeah, I know. And CERN was the ones that created it. There's also, I've heard the story that CERN was a significant part in creating it because they wanted to pass information back and forth to their scientists while they were doing experiments at the collider. I don't know how true that is, but that's what I've heard. So who knows? The internet was created either way. We've all enjoyed it for 25 years. Why all of a sudden are countries in Australia, Britain, they're locking it down. The States is talking about it now. Canada's working on it. So if they lock the internet down, let them have it. I don't care. There's other ways of getting information out.
Well, hopefully it doesn't get that dystopian, and let's
We're
share
getting
what we
close,
can
my
while we
brother.
can.
We're getting close. I'm telling you.
Let's
Carney's
fall
coming.
back to the BBS chat rooms.
Yeah, you could do VPN. Definitely. Until they outlaw them, definitely you could use VPN.
If you
No,
have a
the
satellite phone, you could get internet.
BBS.
There's other ways if you're using satellite.
But you know what? How does that affect global commerce? Because
Oh,
everything's done
no.
through the internet.
Well, they've already done it in Australia, and I think it was Britain, or it might have been like England altogether. I'm not sure. But apparently there's a big stink over it. We're not hearing it, of course, because of how, closed off info is. But they're trying it in the United States, and I already know that they're trying to pass Bill C-63 in Canada again. Carney's pushing it forward, so we'll see.
Do you know what would be fun? Like to test out all different variations to always find like that they're lagging on whatever they have. There's a different way of doing things. They just don't understand. Like it's tweaking one little thing changes the whole path or the whole algorithm of whatever they predicted, you know? So it's kind of funny. Like for example, a satellite phone.
Yeah.
Yeah, you could use it to transfer cryptocurrency. And
Or
like you could use the satellite to ping that,
Or you could have an ether phone
Okay.
that can't be detected. And if you have the encrypted geographical coil that it connects with, nobody can tap into that.
Quantum coil. I like it.
Just saying. Maybe something like that works. I don't know. Ask Cal Putoff.
That would be really cool. Like it's like I know like walkie talkies have something like that, but still those could be intercepted. But
Yeah.
if it's an end to end, connection that can't be tapped into, the other one is just anybody could tap into that.
Yeah.
Like
But
opposite.
if it's quantum,
That's
well, if
cool.
it's quantum entangled, nobody can tap into it whatsoever.
Man,
It's
you know how
impossible.
much like geolocation has to be incorporated in its structure because
Mm,
it matters. Like wherever.
depending on the system that you're trying to create or how you're using it, I would agree.
Yeah, because you've got
Some say it
things.
can't be done without mass amounts of power being used. I
Mhm.
disagree in that 100%.
Like latitude and longitude matter when it comes to you know, where these two like coils would be located. And, you know,
No, not in this
Mm.
system.
Okay, well, maybe
Yeah.
I'm thinking of a new layer, you know, of a specific, you know, where really nobody could tap into something like
Think
that.
of it
You
like
know.
if you had a coil, this is a thought experiment, of course, right? So if you had a coil system that acted like an antenna and sent the signal, but the information actually came through the ground. When they connected, that charge separation would come together, be like quantum entanglement. Only the two people that have those very specific coils can talk or exchange information in any way, shape, or form through those two. You can't you can't break it, you can't smack the lock, you can't cut into it. There's no wires, you can't tap it. There's no radar that can connect to it or a satellite that can observe the frequency because it's quantum entangled. What this one does the opposite way, like a mirror. And what this one does, the opposite mirror would do over here. So if you understand that language, you can talk in that way and nobody would know you're talking. That's quantum entanglement. They say it's faster than light communication. I think that's a load of crap, but whatever. That's just my opinion. I've been wrong before.
Isn't that like Morse code stuff too, in a sense? Like they,
Kind of.
you
Think
know,
of it more like radio. When you connect to the frequency from where that station's coming from, right? Except the only two people are the station that's giving it and the one that can hear it, the very only one that can hear it. And that's basically how they're entangled. I don't know if I answered that question correctly or not.
Well, that's good. That's good. Oh, oops. And we got Ben's got to head out right away. So let's hear Ben. Look at what
Ben's
we
got that
here.
video he said he was going to show me.
Yeah, I just got a couple of quick videos. I wanted to show everybody the refresher video of what
Hey,
I've been
Ben,
working
good to
with.
hear from you, buddy. It's been a while.
Oh, thanks, man. I appreciate that.
Okay, sorry to cut you
Yeah.
off. You go ahead.
Oh no, you're good. So
Welcome
I'm
back.
still working on my prototypes. Still trying to open the coil shop. But I've been testing the open circuit method. I got the closed circuit worked really tweaked really good, but the open circuit has eluded me, and I fried 2 of my prototypes. So I got to make some more this weekend. But I wanted to give you a refresher on how the system works. Just a quick video of my synthetic AC hypothesis. How do I play this? Oh, there we go. Now, real quick, we're just comparing the waveforms to show you that the lumen lamp in this coil specifically isn't producing the same effect as the synthetic AC that's going on in the Lightning Thief. And you'll notice the 2 different waveforms in a minute. You'll notice the 3 defining characteristics of the synthetic AC waveform are not present in the lumen lamp. This is the Lightning Thief.
Oh yeah.
That's an interesting waveform.
Yeah.
Right.
It's like there's a
When we-
center point.
Yeah, I don't know what it is. I just called it a convergence point because that's what it looks like. But you zoom out a little bit, you get all these harmonics, but that's just one waveform bouncing off itself.
Badass.
Then look at that smooth sine wave that is producing out of all that chaos.
Yeah.
No, I've done the probing for the input and output, and you do see slightly more output, just above, like, it's purple on the output probe, so you'll see the purple just slightly more pronounced, like it's a little bit more on the output, just slightly, which is really interesting. But that's what I've observed, anyways.
Nice work, Ben.
Very nice work.
I appreciate that.
Good to have
So
you back.
yeah, some interesting stuff. And again, I could be wrong in my theory, but I'm just forming this theory based on my observations. And I had the theory before I saw the waveform, and the waveform just kind of adds evidence to the theory, in my opinion. But I am doing the podcast again. Benefactor's Guide to Free Energy Devices will be weekly. And I'm not sure which day, because I do have a full schedule on my daytime job. But I will be going over my ideas for stepping down voltage using the Rodin coil, something that has not really been discussed in the Rodin coil circles. But I do have a working theory. So if you're interested in that, stay tuned. So also, I found this video that gives a little support to Gerald's theory. And I want to play you Gerald's theory, right? Because I made a video a while ago of Gerald's theory. So it's very short, but I'll show you. It sums up his theory pretty nicely because he's narrating it. Give me 1 second. No,
Oh dear,
pop it
yes,
open.
please. Is this Gerald AI or is this Gerald?
No, this is Gerald IRL.
Get myself into trouble here.
Oh dear. Oh dear, eh?
All right, so this is it's an oldie but a goodie.
Perfect. Oh, we can't hear the audio on it. You're gonna have to reshare it and select share audio on at the same time.
Can't hear the audio?
No, we
Nope.
could not. So you'll have to end share and then reshare and make sure the share audio option is on the tab. Darn StreamYard.
Yeah, give me 1 second.
No
I'm gonna
worries.
use Chrome.
Okay, so you will be back then. While we are waiting for Ben to switch over, I just wanted to point out this is the jar with the monoatomic and nano silver. That's the base of it with like the clusters. So when you are seeing all of the spirals here forming, that is clouds of self-organization above in the structured water.
That's
And
cool.
this is what it looks like once it's actually settled. So,
I like the other picture. That one looks like soup.
right? So definitely don't eat that stuff. Toxic AF.
Absolutely.
And here I've got some triple solenoids around tungsten electrodes, activating them into the red and crystal states. Good old Bert and Ernie. Okay, and then again, this one's actually a double vortex spiral forming. You can see the two.
Oh, yeah. That's cool.
They form every time I just disturb the water a little bit or put a little bit more in, and they go into the self-organizing galaxies in a jar. And a bit. One always turns bigger and like consumes the other when there's two.
Yeah, usually how it works. I see that in a different experiment, and it has nothing to do with alchemy or chemistry.
Right, it's
see
just
that in
the symmetrical geometry of micro to macro.
Could be.
How's the vortex go? And it's like Was this the witches and wizards' little cauldrons of seeing things? I don't know.
Oh, interesting thought.
Could they be portals? Could be. All right, sorry. There we go. Back to Ben copying Gerald's thesis.
Can you hear it now?
No.
No.
Not yet.
No audio. You're gonna have to try one more time, and there should be like a little switch at the very bottom of the share tab, and make sure the tab you're sharing is the window of the Chrome as opposed to the screen, I believe, because that.
Oh, yeah, it says to share
Yeah.
audio, share a tab or screen instead.
There we go. See, we worked through it.
Yep, there it is.
Dun, dun, dun.
There we go.
Professional
So mine
streamer.
worked too.
I see the audio button. We're good.
Possibly
It
be a
was a sound
resonance chamber.
It was a sound chamber.
There we go.
When all that started to happen, you got to think when voltage breaks water, there's sound and it starts to echo, right? And that echo would vibrate the king's chamber. And because of the way that it's built, there's like different tones that go throughout the whole pyramid, pushing that energy all the way up. There's a couple more details that have to be added. But as far as I'm aware, because of the way that the pyramid worked, the whole base around the pyramid, there was temples that were built in front of the pyramid, behind the pyramid. And these are what the Egyptian priests used. And they had an ankh that would sit hanging on their waist. And everybody thought it was a religious item. Well, perhaps it was, but it had a lot more significance than that. So these temples,
technology?
Yes, it was. It was actually a tuning fork, but it was a special tuning fork. So these chambers or these temples that were at the base of the pyramid, they had 2 rooms in it. And let's say they referred to them as slaves. I don't think they were slaves. I think they had incentive and actually got paid. So one of the slaves, let's say, broke his arm. He'd come to the priest would go, okay. He'd look at his charts, he'd go, you have to come back at 2 o'clock in the afternoon. Because the temple that he would bring them to had slits all around the very top of the temple so that the sun could come in at whatever angle at that time of day was needed. So at 2 o'clock, the person would come in, he would sit in the bigger room that was an echo chamber. The priest would go in the smaller room behind him, and there was a square that went between both rooms. That's where he put the ankh in. And he would smack that sucker, and it would vibrate throughout that room. The light coming in would come down at a certain angle, hitting the person who sat on that seat, and would give them the frequency of light, sound. And here's the beautiful part. Because the pyramid would cause the area all around it to have a negative energy because the way that it would charge, separate the whole environment, those people that were sitting in that chair would get enveloped with energy, vibration, like energy witches, vibration, light, and sound. And what would that do? A broken arm takes about 6 weeks. When the priest was done with him and he left, 3 days later, he'd be back to work.
So recently I was scrolling through social media and I found somebody actually made one. Check this out.
There we go.
Listen to that.
Wow.
Very nice.
Oh, there's so much more to it than that. And I freaking love that. Especially the way they built it, how there was 2 posts that came down. Now think about those stones. They all find them with 2 holes, right? I wonder why. Get my point?
Yeah, it's very.
Doesn't it look like that code that they sent back supposedly through some crop circle where the human head is open to the universe? Like, do you
A
see that
little bit. I
opening
know
look
what
like
you're
a
talking
person?
about. Yeah, a
Yeah.
little bit.
Oh, just
Yeah,
kind
an
of.
ankh is a very specific thing. It's a special item. I believe it wasn't just a tuning fork, but the tuning fork factor allowed bringing sound into those chambers for people to go through that process. Not only that, I believe that the ankh was responsible for applying sound to the stones that goes to the theory that they levitated them into place. Not sure on that one, still working on that one, but it's an interesting theory. So
Indeed.
when I get it fully complete, I'll definitely bring it out more.
You know, I always wondered the composition of the stones. Is there a metric of the increase something and decrease something so it has like units of ladder measurements? Nobody has ever tested like two stones or a stretch of stones, you know, for like, you know, the composition exactly. Is it a little bit more of this, less of that? Is it the, you know, the ones on the top? Are they different, you know, structure? Like, you know?
I can
Would be
tell you
just
this: I know how they made them nice and beautiful, shiny when it was
yeah, the
all said
limestone.
and done, right? Well, we
Yeah.
all do. It was sodium silicate, but I've done like multiple tests on building different blocks and bricks, and if you get the formula right and you energize them electrostatically, they pull together like magnets. They actually become like 2 to 3 bricks became one the minute I charged them electrostatically. I think it was 3. I have to look at my notes. It's been a little while since I've played with that. I've been really busy on other things. But I had said before I was building a pyramid out of geopolymer. And I was playing with different sizes, and I was going to build it 3 feet tall. But I ran out of sodium silicate. I had problems. So I've ordered a bucket, and the bucket came solid, rock solid, and they're not going to return my money. So I'm going to order a small container and do a small version of it. But basically, when you get the mixture right, they act almost magnetically, although they're not magnetic. I don't know if that makes sense to any of you out there.
Yeah, they're atomically polarized. It's something I'm working on. I like that.
You could say that, yeah.
Well, it's been fun, everybody, but I gotta go to bed.
Much
You have a
love.
good one, Ben. It was good talking to
Take
you.
it
Thank
easy,
you
Ben.
very much for that video. I
Very
appreciate
good.
that.
It
Yeah,
was
no
awesome.
problem. I wanted to make sure you saw it because I thought it was really cool.
It's
It's
awesome,
epic.
dude. I want it on my channel.
Thanks, Ben. Good
Have
to
a
see
good
you
night,
again.
everybody.
Man, don't
Good
be a
night.
stranger, Ben. Love you, brother. Good, great work as always. Before we end, we got a first-time guest with us, Christopher, and been sharing some of your work with me. Do you want to maybe go over what you're doing quickly?
Could you hear me? You can hear me
Yes,
all
sir.
right.
We
You
can.
do hear me. Okay.
Yes.
I'm like, great. And once I figure out how I can share this, let me get. I'm CBK Wahoo. Christopher, nice to meet you all.
Oh,
And
nice.
I've been in
pleasure.
the community for a long time now, in the chats and following along with everybody else, with Dan
Yep.
Winter and Bob Grenier and all the rest. And it seems like everybody's on the same page right now with the harmonic resonance stuff. And I'm coming, and that's where I come in, because what happened to me is I became disabled with a couple of car accidents, and to make a short story, a little shorter, you know, how I came into about doing this. I went and I couldn't afford. It was one of those riff machines. I wanted to buy a riff machine to heal myself, so I couldn't afford it. So what I did was took a Tesla coil and decided to put a orgonite pyramid, a custom orgonite pyramid, and put it on top of it, so I can be able to pulse custom frequencies through it, and use that as an antenna to pulse PMF, PEMF. You know,
I know exactly what you're
one
talking
with
about.
the and I built it through the George Lakowski, what else? Tesla, and it's Wilhelm Reich. It's all their works together, pretty much.
Yep.
There's one more, Royal Riff, Raymond Riff. That's the most important one right there.
Raymond Royal Rife. Yeah.
Yeah. So it comes to short. I ended up building this thing because I wanted to. Have you ever heard of the Q? It was a cheat coil. It was a cheat coil. It's like a road. It's a rodent coil where you can hook to your telephone and play the frequencies through it. Right? You pulse the frequency through it, and then you put it on you'll be able to put it on your body and everything, and pulse the frequencies through your cells.
Are you talking about the Matthew Rife coil?
No. This is completely different.
Coil. No, it's cheat coil.
Yeah, I think he's like associated with Dan Winters a little bit, but I also believe they're going to be at Tesla Tech as part of the trade show aspects.
Yeah, it's all similar though. It all has the plasmoid. You have the frequency generator, and then you have the coils, of course, and then the antennas to where you can direct the energies from this. So what I did is I built a few prototypes, and the first one worked great, and it achieved exactly what I wanted to. And how do I share this or put a screenshot
bottom
of
the screen, there's at the bottom of the screen in the center, there's a couple buttons, and there's one that has a plus sign on it. I click on that one, and then share screen, and then should give you the tabs first for Chrome, or then window or screen, and then you just select which one.
Yeah, let me see if I can pull up. I'm gonna pull up a basic picture of it. If I can pull that up, so you know what I'm talking about. You actually see the device. Let me see here. I'm looking here. Yeah, bear with me. Like I said, I'm a noob on the sharing the screen stuff here.
All good. Walk you through it.
Let me see if I can get it. Once I get it, I'm a fast learner. I'll get it.
And you got it. Boom. Oops, no. What? Oh, what? Wrong. No, there we go. There we go.
There it is. Okay. All right. That's it with it running. Can I do like 2 or 3 at one time, or just do it one? Is it just one at a time?
It depends on the tab that you have it open with. If you can switch pictures in that tab, it should work. Otherwise, you'll have to close and reopen.
Okay, I'll figure it out. Yeah. So this is with the bulb is the plasma point on the top, which you're seeing the blue green, and that's sitting on top of the geometric orgonite. I have here the orgonite, and the little lights, the neons that you see, are just so I can see that it's on and functioning, and of course the bulb too. That's what it is. And then the coil, it's sitting right on top of the coil to where the program frequency generator, which you can connect. It connects to your phone, or you can use a tablet, and then also it's a free download app that I use. Frequency generators, which is it's Z app Riff, and it's a free download. It's got all Royal Riff. It's like the Spooky 2. All of those combined, like 3,000 plus frequencies that you could run through that for free download. Like I said, so I did that, and that's what I have here. Let me see if I can get a better picture with the coil, with the actual coils on it. Let me see if I can kill this one. This one here.
Yeah, I got that Z app
got that.
myself.
Let me get another one. Get this other one here. This one that I'm looking for, the pick has the dual coils. So you're 2 Tesla coils to where you can set up the dual harmonics, one on each side, and you pulse it just like Dan Winter has done all the work on this already with the conjugate waveforms and stuff. So he has all that documented. So what you do is you take one of these. If I can find the picture.
Not sharing. If
I'm still looking for it.
Gotcha.
Yeah. What? Now I lost my train of thought.
Talking about the
All
dual
right.
coil.
Yeah. All right. So the dual coils, to where you can set them up and run the harmonics of them, which there's, the multiple for the healing purposes, which you want to even say that on YouTube about that. And we're not going to make any, what do you call
Energy
it? We're not going to make any claims about that.
field,
Right.
right? It's your spiritual life energy force.
We all know about
key,
that.
right?
Hold on, I'm gonna find this. The pictures are so small when I'm looking on this thing, it's hard to find the picture, is what I'm having the trouble here. All right,
No
I got it. I got it. There we go.
Very
There we
nice.
go. Okay, so there we go. So there you have the coil on the left, 2 coils, and then where you can run, you hook up your and run the frequent. And the main one I have was actually a pyramid. I don't have that in the pic, but these are the geometry. You have the saucer, which is the deglock. You call that the deglock if you want. And then you have the flower on the left, the flower of life. I call that one. And then of course the pyramid. So I have 3. There's 3 of them that I have to. This is like third and fourth generation prototypes already I'm into. And then this is where the harmonics come in, because originally I was just using 1 coil. So the whole purpose of this, like I said, I wanted to be able to pulse frequencies out of this thing and reset my cells through all these works of Lakowski's works and all the rest of them that I've done the research on. And it's working to my extent. I've been using it about a year. I think it's been about a year. And that's what it is. And the Ankh, also, this is a part of it. The Ankh in the middle is also custom orgonite, which has the components, electrical components in it. It is a functional oscillator Ankh, kind of like what you were showing with the earlier video with the Ankh, where you have the it's actually an oscillator. Is actually exactly what it is. It's a frequency oscillator. So that's like an extension of your frequency when you hold that in your hand, and along with the frequencies, and then of course it goes with the Waz scepters, which is the ground rod, your grounding rod. So what I'm getting at is I want to build these small scale, and be able to explain and show how this stuff actually works, and that's where I'm at. I'm at right now with this.
Looks really cool.
Yeah, and
It's amazing.
this is totally scalable to, customization to infinity. Here, bigger coils, different bulbs, customizations that you can do this. This is just the basic stuff. The least expensive way I can build one of these devices equal to the Spooky 2, and also Dan Winter's Phi Ray is very similar. It does the same thing. It's exactly the same thing, functions. It just looks different. Is what I have. So that's pretty much what I have and what I'm working with. So, and I want to be able to get in here and build with some great people and great minds here, like everybody else is doing. So that's where I'm at. Here I am. Let's build.
Right on.
I can explain how to use these and what their purposes are, which I believe probably everybody already knows is pretty much what they're for.
See,
Mike went said that
I don't want
Dan
to make too
Winter-
many claims on that, though. You don't want to go that route. You know what I mean?
exactly.
We don't want to go that route.
What you've done is absolutely awesome, because there's also the other guy making coils with the same last name as Royal Raymond, and he sent me one of his original systems. That's why I have the Z app, and it's like
Nice.
all of that stuff works wonderful, but the coil geometry and numbers of the first one are not it just, the moment I turned it on, it was instant pain, and I was like, nope, not messing around with that one again. But with what you've done, I would love to either replicate the coils you're working with and the orgonite system, or order one from you to connect to every other aspect that I got off of Rife, that I can then use those same frequencies.
Yeah. That's what all the data I have. I'm willing to share all the stuff that I've come across for the past 10 years. I've been working on this stuff for a good while. I've been a finished carpenter building homes from the ground up for 27 years, and then when I had my accidents, this is what I wound up doing. So pretty much I'm technically going into electrical here from finished carpentry. So I have the building skills and now with the electrical and all that. And I guess you might as well be an engineer too, because if I'm engineering and drawing all this stuff out, I read plans for a living. So I know and see all this stuff. So, and I've got a lot more, stuff besides this that goes with all of this. It's just, this is a good start here. Anyway. Yeah. It's silent.
Yeah, no, good work. That's awesome. I love that.
Oh, I was going to say to crypto, you can use this and put a couple of these on each side of your jars of materials and pulse custom frequencies. I was going to suggest to use these to pulse custom frequencies into that.
What I've been waiting to do.
Yeah.
Exactly
to add this
what I want to do. So yes,
yeah,
you got to I got to replicate your system here and get on.
I got one more good one that goes with Nathan's work and the way he's designed his coils. That I have an idea that I'm going to pitch, and once I have it drawn out correctly, it's pretty much technically two induction coils. One, you set one on top of each other, and then in the middle you'll have a cosmic egg, either blown glass, custom blown glass, or whatever material you want to make it out of, like similar to the thunderstorm generator, to where you'll have that in the center as the core with either some mercury or some other metals or whatever materials in the middle of it that will, which mercury I think is the best.
From gallium from Phil, huh?
So you have the induction coil on the top and the bottom, and it's going to spin that, and it's going to create the electricity inside that cosmic egg in the center. And that's what I want to work with Nathan and you to work on and design this. So I don't care who builds it. You know what I mean? I don't to be first or none of that stuff like that. As long as it gets built and it works, it doesn't matter.
It's a team effort, right? So it's that we all build it together, and when everyone builds it, replicates the experiments, then
that's why thanks for letting me come on and share this with you guys. I surely appreciate it.
Our pleasure. Glad to have you, and to come back every week, because we got to develop this. This is amazing.
Yeah, awesome.
It was a good show.
Yeah, that's what I got. Once I'll get a little better presentation. That way I can, show more stuff. And once I get used to this, it's so far so good. I got my what do you call it?
We popped Chris's StreamYard cherry
issues out of the way. Yeah. Yeah, there you go. Cheers. Happy Friday and happy weekend. Yeah.
Absolutely.
We're gonna build some cool, I'm ready to build some cool stuff. Yeah. Can I gotta get rid of it? Yeah, let me get rid of mine.
Yeah, just a joke, team effort. You have all the managers and the one guy in the middle that builds everything.
We're the opposite. That's government work, and we are the opposite here.
That's absolutely government work, yeah.
Just a joke.
Okay. It was a great show, guys. Just a reminder, everybody, we go live to air again next Friday at 9:00 Eastern, 6:00 Pacific. I guess, Bernie, we're going to wrap it up. I'm camping here in the middle of nowhere. And,
good for you, Mike.
Yeah, I'm out camping right now.
Sasquatch.
Yeah.
And still doing the show. Man, you're a trooper. Yeah. Trooper.
Exactly. Yes, man.
Amazing. Well, thank you for co-hosting and running it with this while even camping. Now get the heck back to your family, and love you all. And I guess we'll see you next week live from Tesla.
Next Friday, everybody.
Okay, take care. Have a great weekend.
Right.
Good to meet you.